Hello everyone, welcome to this session. I'm Solale Tabarestani and I'm presenting our paper entitled as Joint Low-Dose CT Denoising and Kidney Segmentation. I will start with a quick introduction of the problem that we have addressed, then I will describe the method that we've presented in this paper and a quick information on the data that we have used, and then we will move forward to the results that we have reported in this paper, and then I will end with a conclusion and the possible future work. As you know, chronic kidney disease is a nation burden to the health system of every country. Computerized tomography is very common imaging modality because it's non-invasive and it has high accuracy when it comes to evaluating kidney problems. Low-dose computed tomography has gained greater attention recently because of the lower dose of radiation that it needs and faster scanning time, which makes it suitable for screening, diagnosis purposes, and follow-up studies. In this figure, normal CT is shown on the left and low-dose CT is on the right. As you can see, low-dose CT has lower image quality and more amount of noise and distortion. Because of this, it is necessary to find methods and algorithms to enhance the quality. Organ segmentation is an important task which is usually a preliminary step for most computer-aided based diagnosis methods and augmenting medical images. Therefore, we have defined two objectives for our research. The first one is image enhancement and the second one is kidney segmentation. With these two tasks in mind, we use the joint learning approach. In multitask learning, we use the interrelation between two tasks to improve the accuracy of learning. In our previous research, reference below, we introduced a deep learning method for image-to-images translation, which is based on conditional generative adversarial networks to perform multitask learning. In this slide, the conceptual block diagram of GAN is shown on the right. There is a generator network that tries to produce a fake image, which is close to reality, and there is a discriminator network that tries to discriminate the real image from the fake ones, meaning that in generator adversarial networks, the discriminator network is playing against the generator. Let's say the generator tries to fool the discriminator. This slide demonstrates few applications of Pix-to-Pix algorithm. Pix-to-Pix uses a conditional generative adversarial strategy for image-to-image translation. As you can see, it can output a pretty realistic image of a cat from the condition of human drawing cat. We have adapted our image-to-images translation algorithm to address the problem of image enhancement and kidney segmentation for low-dose CT modality. It means that the generator network produces two outputs from the input low-dose CT slice. The two outputs are two slices. One is the enhanced LDCT with a quality close to the normal dose CT image, and the other output is the segmentation mask of the kidneys. This algorithm falls into supervised deep learning methods, meaning that the labels, including the segmentation mask and normal dose CT slices, are provided to the system. The discriminator network produces two output matrices, D of R and D of F, corresponding to the real and fake input tensors. The fake input tensor is a concatenation of input and output images, and the real input tensor is the concatenation of input and target images. If the discriminator is trained perfectly, it will create D of R matrix of 1 values and D of F matrix of 0 values. On the other hand, if the generator is successful in fooling the discriminator, D of F would be a matrix of 1 values. The loss functions for training the generator and discriminator are expressed in these equations. In the training phase of the network, for each batch feeding step, the generator generates output images. The discriminator looks at the real paired tensors and the fake paired tensors and produces an estimate on how realistic they look, D of R and D of F. The weights of the discriminator are then adjusted based on L of D, and the generator's weights are then adjusted based on L of G. For evaluation purposes, we use the multi-atlas labeling beyond the cranial vault dataset. This dataset is consisted of CT scans from 30 labeled subjects. In order to produce low-dose CT scans, we use the approach introduced in this reference. For evaluation, we use 7-fold cross-validation on subjects. We have two tasks. For segmentation, we compared the result of our proposed method with 2D UNet, Pix-to-Pix single task, Pix-to-Pix multitask. For denoising, we compared with WGAN MSE, Pix-to-Pix single task, and Pix-to-Pix multitask. All those methods are 2D and processed slice by slice. The first interesting observation of this experiment is in the convergence ability of different networks. While the denoising problem is simple and all the methods for all folds converge properly, the segmentation problem is found to be very challenging and makes the networks to converge to improper points. This table shows the number of successful folds of different methods for both tasks of segmentation and denoising. For the segmentation task, the 2D UNet was successful for all segmenting folds on the ND-CT set, but it was completely unsuccessful for training on low-dose CT sets and stuck on the local minimum point. The top figure shows the loss curves for two same training folds of UNet on ND-CT and LD-CT. The below figure shows the segmentation result by UNet on ND-CT left and LD-CT right for the same slice. As you can see, training on LD-CT converged to background class only. In addition to the noisy images of LD-CT, the target classes of background, left and right kidney are highly unbalanced, which makes the problem even more challenging. As it is shown in this table, for the segmentation task, the Pix-to-Pix single task and proposed Pix-to-Pix multitask are converged properly in 3 folds and 5 folds. Pix-to-Pix single task is better than UNet because of its conditional generative adversarial nature, which makes the network to have more chance to escape from the local minimum. On the other hand, Pix-to-Pix multitask is better than Pix-to-Pix single task because the denoising task is augmenting the whole system through the regularization mechanism and finding a solution on a small area of representation at the intersection of both tasks. This figure shows the loss curves of training for a converged fold and misconverged fold via Pix-to-Pix space method. The figure also shows an example of the achieved segmentation results, which is on the bottom. Notice that if the Pix-to-Pix space is not successful in converging, it means that the discriminator wins the challenge and the generator cannot produce enough accurate outputs to fool the discriminator. In this slide, the top figure shows the segmentation and denoising results by Pix-to-Pix single task and Pix-to-Pix multitask over a low-dose CT test slice. The bottom figure shows the results of denoising tasks by different methods of WGAN, Pix-to-Pix single task, and Pix-to-Pix multitask over a low-dose CT test slice. This comparison clearly shows the superiority of multitask learning over single-task learning. This slide shows the quantitative comparison of single-task learning-based methods with our proposed Pix-to-Pix multitask learning method. In the top table, the average DICE score and false positive rate over 3 overlapped successful folds is shown for the segmentation task, and the below table shows the average root mean square error and a structural similarity index on 5 overlapped successful folds for denoising task. Organs in the CT image modality are 3D, therefore instead of 2D CNN in our method, we are planning to employ 3D CNN and we expect to result in an improvement. Thank you for your listening and we are looking forward to any questions that you have.